All right, so we learned how to add matrices, subtract them, and multiply them by other matrices. And when we did all those things, the results were more matrices. And just to review, if I multiply a 2 by 2 matrix, 2 by 2, by a 2 by 3, this is a 2 by 2, 2 rows, 2 columns, and I multiply that by a 2 by 3, then I can do it because this is the same as this, and my result will be this by this. I'll get a 2 by 3 as a result. And basically, the 2 and the 3 go with the 1 and the 2. 2 and 3 go with 1 and 2, and you get 2 plus 6 is 8. Then the 2 and the 3 go with the negative 1 and the 2, and you get negative 2 plus 6 is 4. Then the 2 and the 3 go with the 0 and the 1, and you get 0 plus 3 is 3. And then I'm done with those. And then I go to the 1 and the 2. The 1 and the 2 go with the 1 and the 2 over here, and I get 1 plus 4 is 5. Then the 1 and the 2 with the negative 1 and the 2 right here, and I get negative 1 plus 2 is, or excuse me, negative 1 plus 4 is 3. And then the 1 and the 2 go with the 0 and the 1, and you get 0 plus 2 is 2. So a 2 by 3 result. So with multiplying matrices, you get another matrix like this. Adding matrices is more simple. With adding matrices, then it's just whatever the size is stays the same. So 2, 1, 0, 2 plus 4, 2, negative 1, 0 equals 6, 0, 2, 2. I think. So you get the idea that adding and multiplying matrices, you get another matrix. What we're doing here, evaluating determinants, is different. You do not get a matrix, you get a number. So the determinant of a matrix is not a matrix, it's a number. And the way you do it is if it's like this, if we look at our matrix as A, B, C, D, then the determinant is AB, or excuse me, AD minus CB. How do you know? So the way there's special notation for it, we put it like a straight bar, so straight bars mean determinant. And so for example, 2, 6, 1, negative 1. So we say, okay, remember it's like a diagonal. So that's our first product. AD is negative 2 minus BC is 6 equals negative 8, and that's the determinant. Okay, interesting thing about determinants, they only work with square matrices. So 3, 1, like that, no, does not exist. And again, the straight bars mean determinant. But a square one like this does work. Just as before, it's down diagonal minus up diagonal. So that's a good way of remembering a rule. Say down down diagonal minus up diagonal. Well, that's easy enough for this one, right? Down diagonal -2 minus up diagonal 6, and you covered everything. But for this one, it's not just this. There's, because you haven't covered all the numbers. It's not just this minus this. You then redo it. It's so, I mean, it is that. So you'd say right there, well, that's 0 minus 0. But then you got to do it again starting here. So you shift over one and go like this, and it's, oh, that's 2 times 2 times, and what goes here? -1 goes here. Why? It comes from over here. So it's like you rewrite the whole first row over here so you can do another set of diagonals. So now you have another down diagonal, 2 times 2 times -1, that's -2. You have another up diagonal, 1 times 2 times 1, that's +2. And then you're going to do it one more time. 3 times 4 times, and what do you think goes right here? You said 1, you're right. 1, 0, 2, that row gets rewritten. So we have 3 times 4 times 1 makes, you see that the diagonal 3 times 4 times 1 makes 12. And 0 times 4 times 2 makes 0. So these are my 6 answers that come from doing 3 down diagonals and 3 up diagonals. So I say whatever the result of the top is, which happens to be 10, minus whatever when I say the result of the top, I mean the sum of all the ones on top, minus the sum of the ones on the bottom, minus the sum of whatever the ones on the bottom are, 2, and my result is 8. So weird thing that works out to help us. It's a weird procedure, but it ends up helping us in certain mathematical things. Amazing little rule. So if you have a triangle in the coordinate plane, and you know the 3 points that are the vertices of the triangle, you can find the area by finding the determinant of a square matrix that plugs in the 3 points in the first 2 columns, and then just plugs in the number 1 in the third column, and you find that the determinant, and multiply by plus or minus 1/2. Now basically, if your result is negative, you would multiply by -1/2, and if your result is positive, you result by positive, because you have to have a positive answer for area. And then you get the area of the triangle. So for example, if I have my triangle here on the coordinate plane just above the x-axis, and that's 4, 0 right there, then those are the 3 points. So I plug the 3 points in any order into this matrix. And I plug in 1, 1, 1 here. And then I find all the downs. So 1, 0, 1 is 0. And then I have to copy the next 2 rows over here. Like this is going to be 1, 4, 6 again. This is going to be 2, 0, 2 again. So I can go down and get 3 values again. So 2, 1, 6 gets me 12. And 1, 4, 2 gives me 8. And then my up diagonals, 6, 0, 1 is 0. 2, 1, 1 is 2. 1, 4, 2 is 8. So altogether, my determinant is 20. I add up the top, minus 10. So the determinant is 10. To find the area, I times by plus or minus 1/2, because that's what it says in the formula right here. So multiply my result. In this case, it's going to be by positive 1/2, because I don't want a negative result. So 5 is my area for the triangle. and you can double check that in your head maybe. You say like base times height. We can see that this triangle has a base of 5 and a height of 2, and so 1/2 5 times 2. Same thing down here. Although this method is better for us in this case because here we'd have to prove that this is a right angle, and I don't, we don't want to do that right now. Okay, so then the other use of determinants besides finding the area of a triangle is to solve systems of equations. So there's something called Cramer's rule, which basically tells us that if we have a linear system of equations in standard form like this, we can make a matrix out of that, and we call that the coefficient matrix. And we can basically solve for x and y by using this ratio of determinants. And basically, your book has written determine DETA, and what they mean by DETA is simply A, B, C, D. And so Cramer's rule basically states that x equals, and then it's almost like this over itself, but the a when you're trying to find x, you replace the coefficients of x with EF, and when you're trying to find y, again it's this, but you replace the coefficients of y with EF. Let me show you an example. So this is number 37 on page 219. And so system of linear equations, we could solve it by elimination or substitution, but we're going to use Cramer's rule. And basically on the denominator, I'm going to have the coefficient matrix. So 7. So this is going to solve for x. I'm going to say x equals. And I got 7, 3, -5, and 10. And up here I'm still going to have -5 and 10. But instead of 7 and 3, I'm going to sub in 11 and -56. Sorry for the terrible handwriting. So the determinant of this top one is 110 minus -56 times -5 is 280. So minus 280. That's the top determinant, right? The bottom determinant is 70 minus -15, which is 85. So my answer, so 110 minus 280 is -170, and -170 over 85 is actually just 2, so x equals -2. All right, so x equals -2. You might want to pause if you want to copy that down because I'm about to erase a bunch of it. And so then y will be the same thing. We'll have the same thing on the bottom, although now we know this is just 85, right? 70 minus -15. But then on the top, now we're going to keep the left side. We're going to place the y values with 11 and -56. And so we're going to redo this side, and 7 times -56, I believe, is -392 minus 33, which is 11 times 3, to get -425. -425 over 85, and that's -5. So y equals -5. So we should have y equals -5 and x equals -2. And if we check that, -14 plus 25 equals 11. And then over here we've got -6 plus -50 equals -56. So yeah, it works. So that's how Cramer's rule works. And I hope we can use Cramer's rule for 3x3s, but those are super challenge problems. If you can do it with 2x2s, you're in good shape.